Hey everybody, welcome back. Welcome to lesson 3 in Unit 9, Kinetics and Equilibrium. So in the last video, we covered details regarding table I on the chemistry reference table, how it's used and how to manipulate it a bit. And today we're going to cover PE or potential energy diagrams. So we're going to talk about how to read them, how to draw them, how to label them, and all this other great stuff. So, good place to start is, well, what is a PE diagram? And so, basically, what a PE is not physical education, but potential energy. So, a diagram that shows the relative potential energies of your reactants, something called the activated complex, and your products as a reaction happens. Well, what is PE? What is potential energy? And so this is stored energy. So when we talk about kinetic energy, we talk about energy of movement. When we're talking about potential energy, it's stored energy. So if you think of it like, oh, hey, we see a lot of potential in you. I mean, you have the ability to do a lot of things, you just might not have done it yet. So potential energy is stored energy. And so these diagrams, so this one or this one, they show you how the potential energy changes as a reaction goes on. So you're starting here, you have this increase and then it decreases, and that's kind of how the potential energy changes in that kind of diagram. And then here we're starting here. So the reaction coordinate, that is time. Generally, when we're talking about reactions, we're starting over here, and you start with your reactants, and then you're going, and you're producing your products. So that's something to kind of keep in mind. And then, time goes on, you start your reactants, end with your products. So as you kind of convert your reactants to products, how does the potential energy or the stored energy change? And these diagrams can help tell us. So again, a potential energy diagram, so a PE diagram, tells us the potential energy of the reactants, the products, something called an activated complex. It tells us the activation energy, heat of reaction or delta H, and if a reaction is exothermic or endothermic. So this little picture can tell us all of that. And so let's kind of dive deeper into it. So before we go into jumping and labeling these pictures and applying these to questions, let's take a step back and kind of define some of these new terms. So, activation energy is the energy needed to kind of start the reaction. Everything needs that, little push. So if you think of, here is a person with a rock. Your reaction, or your final product, you want this rock over there. But before this rock can get to the other side of the hill, someone has to push it up. So starting that reaction, pushing it up to the top, getting it to have all the potential to do what you want it to do, that is your activation energy. So the energy needed to kind of start that reaction. Now, once you have that rock, or that, stay with the rock example, once you have that rock on the top of the hill, it's kind of sitting there very precariously. This is kind of our unstable, we can call it a transition state. We can call it our activated complex. Activated complex. And that's kind of our mix between things. So here, was our reactant. Here is our product. And that middle section, that's that unstable transition state activated complex, that kind of halfway spot. Now, once it gets up here, the rock gets up there, and it makes it that far, it goes down, and the rest of the reaction is able to happen. If you stop pushing your rock, I made a different color. If you stop pushing your rock halfway up that hill, it's going to fall back down and nothing's going to happen. So in order for a reaction to happen, it needs to hit that top part. And then once it hits that top part, it can then follow through and do whatever it needs to do. So when a reaction happens, the particles that are being involved, so your reactants, need to collide with each other with proper orientation. So they need to be facing each other the right way and have absorbed enough of that activation energy to form that middle state, that middle activated complex. Again, not enough activated energy, not enough energy being absorbed, it will not go. So we're going to talk about this part more in a few lessons, that is collision theory. But again, activated energy is the energy needed to kind of start that reaction. Okay. Next, we kind of talked about this a few videos ago, heat of reaction or enthalpy. So, reminder that heat of reaction is our delta H. And so we're going to see a word later on this unit that looks very, very similar to enthalpy, but it's different. I like to think of it as this. I see the H in enthalpy and I see heat. Because the other word will have a very similar technique. Now, heat of reaction, when we talked about in previous units, we've seen delta, it's the change. So if we're talking about delta H, it's the change of heat energy in a reaction. And so when we talked about, let's say, delta T for our MCAT equations, it was final minus initial. But in reactions, technically, our product is our final, because that's what we're ending with, and your initial is your reactant. So you're still using that same kind of concept, final minus initial, but we're going to use the words product and reactants. So we talked about this a few videos ago. If your delta H is positive, that is endothermic, meaning energy was absorbed. And so your P of your products, so again, your products are on the right-hand side. And if you're ending higher than where you start, that means you have absorbed energy. Now, oppositely speaking, if you have a negative delta H, that means it's exothermic and that energy is released. So your products, where you're ending, is lower than your reactants or where you start. So delta H, again, is that difference between our products and our reactants. And so it's this middle section in between, where you start and where you end. So again, if you are ending higher than where you start, that's endothermic. If you end lower than where you start, that is exothermic. And so this difference in between these two values, that is your delta H. Okay, so here is a blank potential energy diagram. First, do you think it's exothermic or endothermic? And so we're going to come back to that question in a second. But let's kind of start here. We have our reactants and we have our products. So if we're going up to this spot, this green line is our PE of our reactants. So our reactants have 45 kilojoules of stored energy, according to this. Now, get rid of that. Over here, this is our PE of our products. So how much stored energy is in our products? So this blue line up to the very top, that is our PE of the activated complex. So right there, that blue dot, that is your activated complex, that middle section. Okay, so now we have a few more things we need to add. We need to add, let me use this color, here. So if you're starting here at this red spot and going up to the very top of it, this is your EA, or your activation energy. So the energy needed to go from where you start to that top part. So that is the activation energy. And the last thing we need to talk about is the difference in between where you start and where you end, so that middle section. And that is your delta H. So these are the 5 kind of things you need to be able to label on a diagram. So let's go ahead and answer some questions. So PE of reactants. So again, that is where we're starting. And so that's 45 kilojoules. You're just looking at the graph. Our activation energy is from here, where you start, to the top. So it's this section. And so would be 103 minus 45, because it's that kind of in between. We're starting at 45 and want to get to 103. And so in order to do that, 58 kilojoules of energy need to be absorbed. If you absorb anything else lower than 58, you will not get to that top part and you will have to start over. Okay, our PE of the activated complex is the bottom all the way to the very, very top, and that is 103 kilojoules. If we look at our PE of our products, again, that's from the bottom to where the products are, and that's that orange line. And if we look, that's 10 kilojoules. Now, the more complicated part is delta H, and delta H is this middle section in between your products and your reactants. Now remember, delta H is product minus reactant. So our product is 10 kilojoules. Our reactants are 45 kilojoules. So 10 minus 45 is negative 35. So that's how we get our delta H. And because it's negative, we know it is exothermic. So remember, exothermic means you are releasing energy, and so that negative sign denotes that. A negative delta H is exothermic. And we can also tell by looking at the diagram that if you end lower than where you started, so you end lower, that is exothermic. If we were, though, to, let's say, end higher, and so this was your new delta H, this one would be endothermic. Okay, and so last kind of thing to add or talk about is a catalyst. So a catalyst speeds up a reaction by lowering the activation energy, so kind of providing an alternative pathway. So a catalyst first does not change the PE of the reactant, so it doesn't change where you start. It doesn't change the PE of the products, so where you end. It doesn't change starting, doesn't change where you end. It does not change delta H, so that kind of middle section between your reactants and your products, that is not changed. And it does not get used in a reaction. So it starts off, it ends, it just kind of is there. It creates that alternate pathway though. And so in this picture, this red line, let me get my red pen, shows you what a reaction would be. Again, we're starting here, we're ending here. And you need this much energy to start your reaction. But if you introduce a catalyst, you're still starting in the same spot and you're ending in the same spot, but you don't have to go up as high. So now that activation energy is lower. So if we were going to add, let me get rid of this pink. We're going to add the activation, a catalyst to here. This yellow highlighter would be our catalyst. Yellow is a bad color, let's use blue. So we're starting in the same spot. We're not going up as high, but we're ending in the same spot. So that is your catalyst. Start in the same spot, end the same spot, but your hill is a little bit lower. And so that's pretty much it for this. We'll practice this. Here's some cool demos that can show this. But next time we will talk about entropy. Until then, have a wonderful